Same model, same bug report, two completely different agents. The first one edits the wrong files, changes too much code, and skips the test and confidently shows to you that the bug is fixed. The second one, however, finds the relevant code, makes the focus patch, runs the test, and catches its own mistake. And at the end, it fixes that mistake, and then it announced that the code is already debugged. So what could be the difference between the first agent and the second one? Because they have the same model, it's not a smarter model. The difference is actually what's everything around the model. What it could see, what tools it could use, what state it remembered, and what proof it needed before claiming the success. That surrounding system is agent harness. And in this video, we will break down 5 harness decisions that separate reliable agents from confident failures. As you may know, the agent is not simply the model. It is actually the model plus the context, tools, state, and a control loop, verification, and an environment together form the agent system. A capable model with weak state management can repeat the same state, and a capable model without verification can create a patch that sounds convincing but fails as soon as it is executed. Model capability does not automatically become reliable action, and this is where many teams make their first mistake. They see an agent fail and immediately assume they need a better model, but in such use cases, the model is not the main problem. This is not only an architectural opinion. I can give an example from SWE-agent paper in 2024. In this paper, researchers from Princeton designed a custom interface for agents working with software repositories. The interface gave the agent focused commands for navigating code, for viewing files, searching, editing, and running programs. Using the models and benchmarks available at that time, SWE-agent achieved a pass-advance rate of 12.5% on SWE bench and 87.7% on human eval fix. The lasting lesson is important here. The interface itself was an engineering variable. Changing how the agent interacted with computer changed its behavior and measurable performance. So for tools, their names, arguments, and outputs, and also their constraint, shape what decisions the model can make. A vague tool such as work on this repository, for example, forces the model to invent its own process. Focused tools such as read this file, or search for this symbol, or apply this patch and run this test target. You get the gesture is basically more specific, create clearer actions and clear feedback. But even perfect tools are not enough if the model sees the wrong information. An agent cannot reason about information it never receives. At the same time, giving it every file, every log, and every previous message is not the answer either. Too little context makes the agent blind. Too much context bears the task under noise. The harness must continuously decide what belongs in the working context. It may include the original requirement and plan, the relevant source files, the latest tool results, and any unresolved failure. After a test fails, the next step may need the failing assertions, the current diff, and change file, of course. It probably does not need all the logs from successful installation. The model should see what matters now, not the entire history of the universe. Then we need explicit state. Do not rely on the conversation to remember whether implementation is complete, whether tests passed, or whether approval is still missing. Those facts need to be stored as a structured program state. For example, the workflow might record that implementation is complete, unit tests have failed, security review is required, and human approval has not yet been received. The next transition should depend on those fields, not on whether the model sounds confident. This is not memory in psychological sense. It's program state that orchestration layer can inspect and does its job. And now we reach the important part. Many apparent reasoning failures are actually harness failures, or at least partly harness failures. So in this reference from OpenAI, they actually mentioned that early progress was slower than we expected, not because codex was incapable, but because the environment was underspecified. For example, assume that the agent opened the wrong file. That action may be a context or search inference failure. Then you see that it repeated the same broken command, and that may be a state management failure. Or you see it claimed success without running tests. That's clearly verification failure. Not every bad outcome means the model needed more parameters or a longer prompt. Sometimes the surrounding system gave the model no reliable path to succeed. It doesn't really help the model. So this is where our open source project AgentCrew also fits into harness engineering. We create a separate video about it, but if I want to explain it abstractly, the open source project project, which is Markdown first workflow layer for coding agents. It routes the work to focus roles, structures, and handoffs between those roles, and introduces the quality gates or human approval when the risk is higher. We need to run a benchmark at some point on AgentCrew, but we did use it for our personal project and we did significant improvements on the results that we got. So the whole purpose of AgentCrew is to address harness engineering, to make responsibilities, transitions, and approval boundaries more explicit. Implementation can be separate from testing. Reviewers should review the code independently from implementer and tests, and humans retain control over merging deployment and risk acceptance. So that's the practical example of harness engineering. Moving important responsibilities out of a single model call into surrounding system. The most important harness component may be verification. The model's confidence is not clear. Completion should be established through the environment. For developing code, that might mean unit tests, integration tests, type checks, linters, reproducible bug steps, or deterministic acceptance checks. For data work, it might mean schemas, constraints, and invariant checks. For an external action, it might mean reading the updated state back from the service instead of assuming the tool call succeeded. Anthropic's engineering guidance makes the similar point. Agents need ground truth from tool results or code executions, along with checkpoints, stopping conditions, sandbox testing, and guardrails, because errors can compound over multiple steps. But verification alone is not enough, because when the agent fails, you still need to know why. A harness is difficult to improve if it only shows the final answer. You need execution trace. You may ask what context was loaded, or which tool did the model choose? What kind of arguments did it pass? What failed? How the state changed? Why did the workflow continue, or why did it stop? Without observability, teams often react to failure by randomly changing prompts. With observability, they can identify whether the problem came from the context, tools, state permissions, verifications, or the model itself. A preprint from 2026 from this year on automatically evolving coding agent harnesses makes this effect even clearer. The researchers held the base model fixed and modified the surrounding system over 10 iterations. PassAt1 on Terminal Benchmark 2 increased from 69.7% to 77%. What they show is that the strongest gains are coming from tools, middleware, and long-term memory, rather than just prompt-only changes. This doesn't mean prompts are unimportant. It means prompts are only one part of the system. When an agent fails, inspect the whole execution process. Did it receive the right context or right tool? Did a failed command update the state? Harness engineering is work of turning the model capability into controlled, observable, and verifiable execution. The model proposes, the harness provides context, exposes actions, records states, controls transitions, and enforces limits, and at the end demands evidence. Better models, of course, they still matter, but when two agents use the same model and produce very different results, the difference is often not hidden inside the weights. It's the system we built around them. Until the next video, good morning, good afternoon, and good evening. Bye.